Okay, so in the previous session, we spoke about some introduction to what is planning, etc., and the different types of plans that we can have. And the first, one of the types of graphs that we will, planning programs we will see today is what is called the partial order planner. Okay, so this partial order planner is called such because when it's actually a regression planner. So a regression planner starts with the goal state and goes backwards till it comes to the start state. So that's why it's called a regression planner. But it doesn't go completely according to the order. Okay, so that's why it's called a partial order planner. So the partial order planner basically starts with um, having just the start state and the finish state. So what we basically do is, if you take this is the finish state and this is the start state. So the plan consists of an incomplete plan. So as you go on, you'll keep adding to this plan, and the plan will still continue to be incomplete. But when everything has been filled in, you'll get the complete plan. So what you do at any particular point in time is you extend the plan. So what you're seeing is for every state that we have, this is what needs to be fulfilled at this state. Okay, so this is the precondition for this state to be carried out. So what you do is you try to see that this precondition is satisfied by using some action at this point in time, whose effect is the precondition of this state. So what we do is, at each step you are going to extend the plan by achieving a precondition C of a step S. And how do you do this? You choose some action or some operator, okay, whose effect has C in it. So this is what is called a regression planner, like I said. So if we look at this particular example that is given here, this is the tire problem. Okay, so at the start state we have the the spare is in the trunk, and the tire which is flat is at the axle. And what we want at the finished state is that you want the spare tire in the axle. So you want to remove the flat tire and take the spare tire from the trunk and put it onto the axle. So this is one simple planner that has been seen. So what we need to basically do is, if you look at the finished state, it has a precondition here. So you got to see how this precondition can be met. So when it says at spare axle, so what is the action such that you will get the effect as at spare axle, right? So then you go through, it goes through all the possible operators. So what you are going to get here is put on spare axle. So if you say put on spare axle at this point in time, that will have some preconditions, and you have to see that those preconditions are met. So the preconditions here are at spare ground and not at flat axle, right? So these are the two preconditions that have to be met. So now the preconditions which are there to be satisfied are these two at this point in time. So you can either choose this one to satisfy or this one to satisfy. So then if you take at spare ground, how do you get at spare ground? You have to remove the spare from the trunk, right? So you're going to use that action. And what is the precondition of that? At spare trunk, right? And this is already available, so at the start state, so that is fine. So if we come to this, the third step over here, the only precondition that is left is not at flat axle. So how do you satisfy this? By removing the flat from the axle. And what is the precondition of this at flat axle, which is already there at the start state? So this gives you your entire plan. So this is a complete partially ordered solution. And you got to have things like before AI AJ, which means that action AI has to occur before action AJ. Okay. So it is a set of actions and a set of constraints of the form before AI AJ. So it gives us particular order in which the plan is to be carried out, or which action to be done first and which action is to be done later. Okay. So this is what is called the partial ordered planner. So this is what we have shown is a very simple example of a partial ordered planner. It could be much more complex than this. Like your finished state itself could have 3 or 4 preconditions, right, to be met. Then how do you carry out all those preconditions? For example, if you're at home, suppose the plan is, okay, the initial state is that you're at home, and the final state is that you're at home, but you bought bananas, you have bought milk, and you have bought something from hardware store, etc., right? So what will your finished state be? Finished state will be at home. It'll have 3 or 4 different preconditions which need to be met. And each of these preconditions you need to take, and you need to see which action to carry out. Okay. So you may see that for the hardware item, you have to go to the hardware shop. For the milk, you have to go to the shop where they sell milk, etc. Right? So you find that you'll have a number of preconditions. And when is the plan complete? The plan is complete when all the preconditions are met in the entire plan, right? And then you'll get a plan from the start state to the finished state. It's possible sometimes that it can fail also, right? Maybe you will not be able to satisfy some precondition with the actions that are available to you, in which case the plan will fail. So this is the partial ordered planner. So next we will study what is called the planning graph. So the planning graph is an automated way of representing a plan in a form of a graph. Okay. So it is a directed graph. So you're starting from the start state. Okay. And you're getting alternate levels of action and state. So if you take the start state, you're going to do the actions on that, and when the actions are carried out, you'll get the states at the next level, and if you do the actions at that level, you'll get the states at the next level. Okay. So you're starting with S0 or the initial state. So these are predicates that hold in the initial state, and level Si contains nodes for each action that is applicable. Okay. So you are going to see what are the actions that are applicable at level S0, and if you apply those actions at level S0, you will get the level S1. Okay. So every level Si contains nodes for each action that is applicable in Ai minus 1 to state Si minus 1, right? So you get alternative levels. So you'll get a state and action, state and action. So you'll get level 0, level 1, level 2, etc. till you reach some type of a termination condition. So let us see what this termination condition is. So Si will contain all the literals that could hold at time I, right? depending on actions in the preceding time steps. So in the preceding time steps, whatever actions you have taken, all of them together will give you all the literals that you can get at a particular time I. Okay. So it is also possible that depending on the actions that you have taken, you could get P or not B. P. That means both of them can hold at a particular level. Okay. If you do one action, you may get P. If you do another action, you may get not P, etc. Right. So both will be represented if both are possible to get with the actions that occur in the preceding steps. And AI will contain all the actions that could have the precondition satisfied in SI, right? So in SI, if you take the states in SI, if they satisfy the precondition of some action, then those actions will occur in AI, okay? One thing that is to be noted here is that this planning graph will work only for propositional planning problems. So if you have something in, say, predicate logic, etc., you won't be able to use the planning graph. So it shouldn't have any variables. So if you have some variable, say x or y or something, which needs to be instantiated at a particular point in the graph, such things will not work with the planning graph. So the planning graph is there only for propositional planning problems. And it can be used like an automated tool, right? And it's quite effective for solving some type of hard planning problems if it involves only propositional planning. So here we have a problem which is known as the have cake and eat cake 2 problem. Okay. So the initial state is that you have a cake. Okay, so that is the initial state, and the goal that we have is that we need to have cake and eaten cake, right? So this should be your goal state, and these are the actions that are possible. There are two actions. One is eat cake, right? So if you eat cake, the precondition is that you must have cake, and the effect is not have cake and eaten cake. And you can also bake cake. So if you have bake cake, it means that the precondition is that you don't have a cake, so you're baking a cake, and the effect is to have cake. So this is a very simple planning problem. So this is the planning graph that we are going to get. So we can see that in level S0, we have cake and not eaten cake. So this is what is true at level S0. Then you look at all the actions that are possible. So if you have cake and you eat cake, then you'll have eaten cake and you'll also have not have cake. And if you also have what are called persistent links. Okay. So the persistence is that if no action is taken from have cake, you'll again get have cake, right? Similarly, not eaten cake, again you'll get not eaten cake. So these are the states that are there at level, or the propositions which are there at level S1. Okay, so we can see that you can get have cake, you can also get not have cake, you can get eaten cake, and you can also get not eaten cake. So these are the level S1, and if we take level S1 and we apply the actions, so if you have cake, obviously with the persistence actions, you will get all these things, right? But if you say have cake, eat cake, again you will get this action here, okay? So we can see that at level S2 you have cake and not have cake, eaten cake, not eaten cake, which is the same as what occurs in the previous state. So what you can do is that if you find that the propositions that are occurring are the same, then you can stop at that stage, okay, because it's not making any difference. Okay, so at level S1 actually you can stop over here. So here we stop at level S2. Okay. So another thing is you have what are called the mutex links. So I will just tell you what you mean by mutex links. So you have mutex links like have cake and not have cake are mutex with each other, right? So, and you also have not have cake and not eaten cake are mutex with each other, etc. Okay, so you have all these mutex links. Okay, eat cake and not eaten cake are also mutex with each other, etc. Right? So this is what is called planning graph, and this is a very simple planning graph which has been taken just to show how the planning graphs actually work, right? Okay, so what is it that we have seen here? Each action at level AI is connected to its precondition at level Si and its effects at level Si plus 1. And a literal appears because an action has caused it to appear, right? A literal can persist if no action negates it, right? So the literal will again occur if no action is taken. This is represented by a persistence action. For every literal C, we add a persistence action with precondition C and effect C. Okay, so for every literal, we do that. Okay, so the C also is put into the next state. And the small square boxes is what we have used to represent that. Okay, so AI contains all the actions that would occur, but also records those actions which cannot occur together, which is the mutex links. Okay, so two actions which cannot occur together, you put them as mutex with each other. Okay, so for example, eat cake is mutually exclusive to have cake and not eaten cake. Okay, so AI also contains mutex links, that is between have cake and eaten cake. Okay, because if you take eaten cake, the result of that is not have cake, and here we have cake, so have cake and eaten cake are mutex with each other. Okay, termination is when two successive levels have the same literals. So we saw how that actually works. So what do you mean by mutually exclusive links, which are also called the mutex links? So mutex means mutually exclusive. Okay, so this can occur both for actions and literals. Okay, so how do you find whether two actions are mutex with each other? If two actions have inconsistent effects, right? So if suppose one action gives one effect and the other action gives the opposite action. Okay, maybe one has have cake and the other has not have cake, then they are mutex with each other. Okay, one, that is one action negates the effect of the other. For example, eat cake and the persistence of have cake, right? So eat cake will have the effect not have cake, and the persistence of have cake will be have cake. Okay, so they are actually negative of each other. Okay, so you can say eat cake and have cake are mutex with each other. And if there is some interference, one of the effects of one action is the negation of a precondition of the other. For example, eat cake interferes with the persistence of have cake. Okay, because if you take have cake and negate it, you will get not have cake. Okay, which is the negation of the precondition of the other. Or if they have competing needs, one of the preconditions of one action is mutually exclusive with the precondition of the other. For example, bake cake and eat cake, right? They both have the precondition have cake. Eat cake also has have cake. Bake cake has not have cake. Okay, so they compete on the value of have cake. One of them, for one of them it should be have cake, the other one it should be not have cake. So bake cake and eat cake are mutex with each other. So this is how you find the mutex links. A mutex relation holds between two literals at the same level if one is the negation of the other, or if each possible pair of actions that could achieve the two are mutually exclusive. So this is called inconsistent support. Have cake and eaten cake are mutex, right? Because eaten cake will have the effect of not have cake. Okay, so something which is mutex at S1 may not be mutex as S2, okay, because you are using other actions that are possible, and they may not be mutex with each other. It's possible to reach that state by using some other action or a new way of achieving it, right? So this is the planning graph, okay. Now once we have the planning graph, what do we do with that planning graph? Okay, so the planning graph actually gives you all the possible ways in which you can go from the start state, okay, and they are a rich source of information because they have all the information possible about what are the states you can reach at each level, okay, I, at each level I, what are the states which can be reached, okay. So one thing is that suppose one of the goal literals does not appear in the planning graph at all, it means that the problem is unsolvable or the plan fails, right? With the actions that you have, you are not able to satisfy the plan that you have, okay. And how we can also estimate the cost of achieving a goal, okay. So what you do is all the literals that you have in your goal state, you see at what level it first occurs, right? So this is called the level cost of the goal literal, the first time it appears, right? So we can see from the previous thing, have cake has a level cost of 0. Okay, so here we can see that have cake appears here, so it has a level cost of 0. And if we take not have cake, it has a level cost of 1, right? And eaten cake has a level cost of 1, etc., right? So we can see in this way when it first occurs, and that will give you the level cost of that, okay. So suppose we have your goal having a number of literals, right, and each literal will have a level cost. So how do we find the level cost for a conjunction of literals? Because your goal will be a conjunction of literals. So like they say, there are 3 methods, okay, what is called the maximum level heuristic. So you take the level cost of each of the literals and see which one is the maximum out of them, right, which gives the maximum level cost, okay. And then you have what is called the level sum heuristics, which takes the sum of the level costs, okay. So if one has a level cost of 1, another has a level cost of 2, etc., you just add them up and that gives you the total level cost. And the third one is the set level heuristics. So what does it do? It finds level at which all the literals appear without being mutex with each other. So it just checks when all the literals appear. That's fine because once a literal appears with the persistence links, it continues to be there at every level after that, right? So this is what is known as the set level heuristic. So we can find the cost of such a plan by looking at the planning graph. And Graphplan, what has it done? It extracts the plan from the planning graph. So if you have a planning graph, how do you extract the solution from the planning graph? So that is done by using Graphplan. Okay. So what you do is you use extract solution, okay, to find the solution, and we have all the goals that need to be reached. So what you do is you need to find the solution by using extract solution from this, which is just an algorithmic thing, okay, which can be done from the graph plan. Okay, so what happens is if you use extract solution, it finds you the solution, or if no solution is possible, it will tell you that no solution is possible and that there is a failure. Okay, so that is how the graph plan actually works. So this one is the planning graph for the spare tire problem. Okay, so where we just saw the spare tire problem, right? That there is a flat at the axle and there is a spare tire in the trunk, and the goal that you want to reach is that you want the spare to be on the axle. So we can see that even though this is a very simple planning problem, we can see how complicated the planning graph becomes, right? So this shows that the planning graph can get really complex for very complex problems. Okay, so it may not be possible to use the planning graph for very complex problems. Also, we saw that it works only for propositional logic, where you don't have any variables which are occurring. Okay, you have only literals, right? What is a literal? A literal is one where there are no variables. Okay, that is what is called a literal. So this is what we can see. Okay, so disadvantages of planning graph, we just saw how it is limited only to propositional planning, and that is quite a limitation, right? There are a lot of problems where you need to actually work with the variables and instantiate those variables with and make it into literals by the end, right? So they can okay, they can't work with the complex scenarios which involves variables, quantifiers, or even non-Boolean representation. Secondly, there is an approximation of the search space. It is an approximation of the complete state space search tree. Okay, so they may not give a complete or a accurate solution, and you may get suboptimal solutions, or you may miss the optimal solution, etc. Right? Heuristic dependency. The effectiveness heavily relies on the heuristics used to guide the search within the graph, right? And poorly chosen heuristics can lead to inefficient search, and you could miss a solution. That is, you can miss the optimal solution. That's the thing. And we can see how complex it is, right? So even though building the graph may not be the cost of building it can still be high. Okay, even though the graph itself, once you have built it, you can use it, right? But building the graph itself, the complexity is very high. Okay, especially where you have many actions and many states, right? So it becomes difficult to use. And maintaining the graph, particularly with respect to mutex relationships, can be very computationally intensive. Another thing is, if you have dynamic environments, so we know what a dynamic environment is. It is that while you are doing the planning, the environment changes, right? So that is a dynamic environment. So in a dynamic environment, it is difficult to use the planning graph, because planning graph actually takes a situation and it builds the entire planning graph for that, which means that it is a static representation and it will not be suitable for dynamic environment. Okay. And of course, like I said, it cannot be guaranteed to give the optimal solution. Okay. It may find a solution that is not the shortest or the most efficient, right? So these are some disadvantages of using planning graphs. And some of the advantages is simplification and representation, right? So if you take a particular problem, you can sort of represent it in a particular simplified way, right? And it becomes easy to find out anything you want to know about that particular planning problem by looking at the planning graph. So the planning graph gives you entire information about this particular planning problem. So it represents it in a sort of a structured way, okay, making it easier to understand it. And it's a sort of abstraction of the search space. So, and it gives all possible actions, all possible states at different levels, etc. Right? Second is the heuristic development, derivation of heuristics. So you can use it to find the heuristics for plan synthesis, and we saw how we can see the cost estimation. Okay, to get a solution to a graph, or what is the cost of that particular plan, right? So if you have a number of plans that are possible, you can estimate the cost and see which one is a better planning problem to use. And because you are reducing the search space, you find that there is some type of efficiency which results in the planning problem. Okay. Improved performance use because of the use of heuristics. It can lead to faster and more efficient plan synthesis. And there are a number of places where this planning graph has been used: robotics and autonomous vehicles, logistics and resource management, game playing, etc. Right? So you can actually find the planning graph and sort of automate the process of getting a plan by using the Graphplan on that. So this is the planning graph. So all the planning programs that we have seen over here, there are something lacking in it, and it cannot be used in the real world. So let us see why this is so. Okay. One is that you can use the concept of hierarchical plans, which will sort of simplify your process. Okay. For example, if you are launching an aircraft, you find that the complexity is very high. So what you can do is you can have a higher level plan, and each of those higher level actions or operations can be reduced to lower level operations. So you could have a higher level, intermediate level, lower level, lowest level, etc. So the lowest level could have, very simple actions like insert nut A into hole B and fasten it with bolt C, etc. Right? But you can have it at a higher level for a person who's a manager, etc., who doesn't need to go to that lower level. So the mechanic who actually carries it out can go to the lower level. For example, if you're building a house, you can have a higher level concept which says build the foundation, then build the ground floor or whatever, okay, build the roof, and then you build the first floor, etc. So you have some higher level thing like that, and each of that can be broken down into smaller things. For example, you can say build the wall, build the floor, or put the windows, etc. And finally, at the lowest level, you can have things like insert nut A into hole B, or cement this portion, or whatever, right? So that is what happens is, if you use an abstract plan, it becomes easier to understand what is happening, and this abstract plan can be broken down into more details later on. Okay, so that is one of the concepts when you carry out planning in the real world, especially when you're talking about very complex situations. The second is that you can have complex conditions. Okay, so suppose you are using propositional logic, you won't have universal quantification. So it's difficult to talk about a particular object or a group of objects, etc., right? Which you can do when you use predicate logic. Third one is that time, you may want your plan to be executed in a particular amount of time. Okay, so for example, if it is a space mission or something, you'll have everything planned out, that this should take this much time, then this should take this much time, and the whole plan should take a particular time. Okay, but whatever planning programs we have seen till now, there's been no such thing as the time constraint over there. Okay, so we just have a number of actions which will be carried out, and you get the final solution. But it could have deadlines. Okay, projects could have deadline that the spacecraft has to be launched on June 17th or some such thing, and the actions that are carried out will have certain durations, right? So you can say that it takes 6 hours to test the some assembly or some such thing. And the steps of the plan may have time windows. Machine is available at such and such a time, or there is only one machine available, therefore these actions must be done sequentially, they cannot be carried out at the same time, etc., right? So this thing is something like the resources that are available. Okay, so all these things need to be taken into account in your plan. So you could say some type of planning and scheduling will have to be carried out. Next is the resources. So your entire plan may have a budget. So you can say that each of the parts of the plan will take a certain cost for it to be carried out, right? So you want it to be done within a certain budget. Okay, so you need to take that and constrain your plan so that you don't spend more than that much of money. Another thing is number of workers available or manpower available, number of resources like assembly and test stations, etc., may be limited. Okay, so you need to take this limitation also into account. Okay, so what you do here is that every action will also reflect what is the resource that it needs to consume. Okay, some of them can be generating a resource, some of them may be consuming a resource. Okay, so it should reflect what are the resources that it consumes and it generates. Okay, and the planning program should be able to handle these constraints on the resources also. Okay, so that is what you need to take into account. So the next session will talk about planning in the real world. Okay, so in other words, how do we take time into account, how do we take resources into account. Okay, how do you carry out hierarchical plans, how do you carry out scheduling at the same time, how do you carry out quantification in some way. So what you say is that only this part of your assembly has to be, the action has to take part there and not in the entire thing, right? So you are using things like predicate logic, you have variables, and you are using quantification like for all existential, etc. Okay, so the way in which that predicate logic statements are written actually takes all these things into account. So, this is what we will study in the next session. So, we'll stop now at this point.